is another way of indexing a NumPy array. In the last video, we saw we can do slicing notation. For example, start from here, end at here, and stuff like so. There is another way of accessing a NumPy array as we have an array A, and we can just give an index array inside. For example, let's say A is one-dimensional array, and then we just give 1, 4, 6. That means pick the element at index 1, pick the element at index 4, pick the element at index 6. So this kind of array inside can be a list or an array that is called an index array. And you can just pick the elements that you want to pick. For example, you want to pick all odd elements. You want to pick first element, fifth element, and 17th element. You can just create an index array and pass it and index and access your elements using that index array. That's possible in NumPy array. Further, you can access different elements using a Boolean mask as well. So Boolean array, for example, true, true, false, false. Wherever there is a true, pick that element. Wherever there is a false, don't pick that element and return the elements that are picked. For example, assuming here that you have an array A, which is one-dimensional array, let's say, assume that has 8 elements, 1, 2, 3, 4, 5, 6, 7, 8 elements. Now you pass a Boolean mask inside where with obviously 8 elements, 8 true or false values. Wherever there is true, so pick the very first value, pick the second value, don't pick the third value, don't pick the fourth value, pick the fifth value, pick the sixth value, pick the seventh value, and don't pick the last value. So that is also possible in NumPy. One thing that is important is if you do this kind of indexing, which is sometimes called masking. If you do that, if you supply an array index or index in a Boolean form, you by default get a copy as compared to slicing. In slicing, you get a view that's a separate copy. You need not to call a dot copy function. It is by default a different copy. And this is a difference between the ordinary slicing that you do. For example, start from 1, go till 50, take a jump of, let's say, 2. If that is your indexing style, that is called a slicing, the return value is a different view having the same memory. However, if you use the array index or the Boolean array called masks, then you get a copy rather than. So which means if you get a new array, you change the elements in the new array using the array indices, you're not getting that change happen to the original array. So that's the difference between slicing and masking. Okay, this kind of Boolean indexing becomes really handy. For example, what if you want to get all the elements that are smaller than 8? One way to do that is just write A and then apply a condition. A is less than 8. Well, A is less than 8 will create a Boolean array, and everywhere where the element is smaller than 8, there will be a true, otherwise it will be a false. Now the inside array is a Boolean array, and you access all the elements with respect to that condition. So it will return all the elements that are smaller than 8. How fancy is that? Further, you can have these conditions in a combined way. There is one difference. There is an AND operator, A-N-D, and there is an AND operator in a different way. So I'm going to discuss the difference of this and this AND as well in this video. So let's go to Jupyter Notebook, our friend, and see how can we play with this masks. So let's say A is again np.range, let's say 100. That's our A. And what we now do is we access the elements of A. We access, for example, the third element and the fifth element and the sixth element. Let's say we want to do that. And that's our B. Yeah. So that happens, let's say. So what B is this. Something that you need to know is if you change the elements of B now, because that's a copy, let's say -4, that change does not happen in A. That happens in B for sure, but that doesn't happen in A. A does not contain any value that is -4 because using these kind of indices, the array index, by default, the result is a copy rather than a view. Further, let's say you have this A and you want to access all the elements that are smaller than, let's say 40. access all the elements that are smaller than 40. So that is possible. Now B will contain only the elements that are smaller than 40, all the elements. Wow. Further, if you want to access all the elements uh, that are smaller than 40, and they are bigger than they are smaller than 40 and they are bigger than 30. Let's say you want to access all the elements that are between 30 and 40. You can just access those elements like so. There is a problem. A dot any, A dot all. What's the problem here? Um, the truth value of an array with more than one element is ambiguous. Use A dot any or A dot all. Okay, this A is less than 40 is a Boolean array. A is greater than 40, that's a Boolean array. So what's the problem? Why can't we not use this? Or what's the problem? We should have used that. So use and yeah, I guess we were missing these brackets because it might be confusing this 40 with this A and stuff like so. So use parentheses. Great. Now B contains only the elements that are between 30 and 40. Now one thing, what's the difference between this particular and this symbol and? The difference is this and, A and the and operator, it is used when both of the sides of this and has one is one object and it has one true value, either true or false. And this particular symbol is used when the left side and the right side can be arrays and each element of that array can be true or false and so. So you can think of this and is used in arrays. However, this is used when both the sides are single objects. So that's the difference. Other variants of and, I mean, the and is like this, that these are the same things. But remember the use. This is used for arrays. This is used for single objects. Similarly, there are other symbols like or that is used this way or that is used that way. Similarly, there is a not. Not for arrays is used like this way and not for otherwise is used like that way. So remember these, the left side kind of symbols, they are used for arrays. The right kind of symbols, they are used for single objects that has true or false values. So this kind of masking is really, really powerful. Later we will see in pandas accessing different kind of data with particular kind of conditioning. That becomes really handy if we are comfortable with these kind of indexing, and that's really powerful indexing. Okay, I've told you the difference here between and. I've told you that this is copy rather than a view. So just bear with me some more time on NumPy, and I will tell you some more truths about NumPy, and then we will move towards another package called Pandas. So before Pandas, more NumPy is coming. Hope to see you in the next video.
Okay, so I think we're doing good so far. We're learning a lot, right? So I just wanted to point out here, I just want to mention to you guys that the solutions that I come up with and the solutions that I provide to you, some of the videos, there can be more than one solutions, right? So even if you are trying with a different solution, but using the same methods that are required, so till then everything is good. Okay, so it's not necessary to solve it by the solution that is provided to you, but the main purpose is just for you guys to understand the method that you need to use to achieve the result, right? So here's another quiz for you guys. We're learning NumPy, right? So this is a quiz. Create a NumPy array A with integers 0 to 100. We've done that. It's pretty simple, right? Make an array B. Store only odd integers from A in B. Okay, so you're supposed to only collect the odd numbers from A and store them in B. Also, only integers starting from 100. So if you have an array from 0 to 200 and you want to start from 100, and which means B should contain all the odd integers from 100 to 200, right? This is not at all difficult. So give it a try. And as usual, we'll discuss the solution in the next video. Thank you guys. Goodbye. Okay, so we had this task. Did you guys try it? Okay, so it's very easy. Create a NumPy array A with integers from 0 to 100, and then we have to make another array B and store only the odd integers from A starting from 100. So let's code this. We have A, and A should contain 200, right? 0 to 200 integers. So we have used a range function before, and we know how to use it. So what would this contain? It will contain integers from 0 to 200, right? Right, 199 to 199, because 200 is not included. The last one is not included, right? So yeah, we want odd integers, so I think, yeah, that's fine. B equals now what were the conditions? B should contain all the odd integers, and they should be above 100, right? So what should we write here? First of all, there are two conditions, so let me just do this first. Now, provided A is odd, right? So that's understandable, right? That A should be odd, and A should be greater than 100, right? So B should contain all the odd integers from 100 above 100 to 200, right? So this should be above 100, 101, 103, and up till 199, right? Okay, so yeah, this was an easy task. So you can practice like this a lot more. You just need to practice these conditions, and it's pretty simple actually, and it's very convenient also. So thank you everyone, and I'll see you guys in the next quiz.
In the last video, we saw masking, which is sometimes called the fancy indexing as well. And here we are going to discuss one more feature of NumPy, which is a very powerful feature called broadcasting. Think, for example, you have an array, let's say 2, 3, a matrix, let's say two-dimensional array, 2, 3, 5, and 9, and you want to add, in every element, you want to add a number, let's say 5. So one way to do that is create another array with 5, 5, 5, 5, and just apply this add operator and you are done. Great. But this NumPy allows you to just write, let's say this is array A. NumPy allows you to just do this particular thing, and this 5 is automatically broadcasted to match with the dimensions of its other operand, and the addition happens. You need not to do this explicitly. And this broadcasting is not just one scalar value. For example, if you have one variable, let's say A is this, and you want to add, for example, this particular column, let's say 1, 3, you want to add this particular column in the first column as well as in the second column. But then you need this 1, 3 to be copied again and make a bigger array, and then you do that. Well, broadcasting allows you, if you just write this as A plus 1, 3, it will be automatically broadcasted to match the size of the other operand. Wherever the broadcasting is possible, there are certain rules to know when broadcasting is possible. It is not possible each and every time. For example, if you have this matrix 2, 3, 9, and you have 4, 2, 1, let's say this matrix, and you want, for example, 2, 1, and 6, 2, for example, if you want to do that, the broadcasting may not happen because in this way, if I want to broadcast this structure should be, if this structure is broadcasted to in horizontal way, the two columns will be added and the addition cannot happen. If it expands to a vertical way, still the addition cannot happen. So this here you will get an error because broadcasting is cannot happen. But in several cases, when you want to add, for example, a scalar multiplier with a particular thing, wherever possible, this broadcasting is possible. And broadcasting is just it's just a feature of NumPy that allows you to not repeat to match the dimension of the other operand to apply a particular operator. It does it by itself. Great. Next, we see some more important functions to know. One is horizontal stack. That means if you want to concatenate two arrays that can be concatenated together horizontally, you can call hstack function, and that will concatenate the two arrays together and returns another array. Similarly, vstack is if you want to concatenate two arrays vertically, if they can be concatenated vertically. Similarly, there is another powerful function, sort, and there are a lot of other functions. These kind of functions, they are called universal functions, and they are very, very, very powerful, very, very fast. Their implementation is vectorized. Vectorized mean the implementation, the all loop kind of layer is deferred to at the compile time, and the things are really faster when you do a vectorized code. So having said that, it is always recommended to not use explicitly for loops to achieve these kind of results. Whenever a universal function is available, use that, because the efficiency of that universal function will be way, way, way more than whatever loop or whatever function you will be writing other than the universal function. So, and by the way, there is another function, concatenate, as well, in which you can specify x's, and it will either act as horizontal stack or either act as vertical stack, depending upon whether the x's value is 0 or 1, whatever. So let's just get comfortable with these three functions just quickly in Jupyter Notebook and see an example of, let's say, broadcasting as well. So let's say we have a function. Let's say we have an array A. A is, let's say, np.random.rand. Let's say that is 2 by 3. And then I just multiply this with 10. Remember this thing, and then we just np.round. We just round everything so that it becomes whole in this particular way. Okay, that's A, let's say. So that's our A. That's the A. Now, if we say A plus 3, 3 will be added everywhere in A, and that happens through broadcasting. Wow. If we do, for example, A plus, for example, np dot arrange, let's say, just 2 values, and then we just reshape it to let's say 2 by 1 matrix. If you do that, then still what will happen is, just apply the parentheses just to show that this should happen first. What will happen is there will be a column that will be added to every column in A, and that again will be happened through the broadcasting. So broadcasting is that powerful. Next, let's see the stack. So let's say this is A. Let's say we have B. That's another array. Let's say np.random.rand. Let's say that new array is 2 by 2. And again, let's say it is multiplied by 10, and np.round, just to avoid the decimal points. Let's say this is B. Now A is 2 by 3 array, B is a 2 by 2 array. If I just concatenate them horizontally, I will get another array which will be 2 by 5. So C equals np dot h stack, horizontal stack, h stack, and I will call these A and B. One thing that you need to know is if you want to call this h stack, horizontal stack, or vertical stack, these arguments A and B that you want to concatenate, you have to give them in a tuple, or you may want to give several values to concatenate together. Maybe you have 10 matrices to concatenate together horizontally. You have to give all these as a tuple inside. Okay, great. Now, similarly, we can do a vertical stack if we want, one on top of the other, and we can call a concatenate function as well if we want. Third is a sort function. For example, um, if you want to use np dot, let's say a is np dot random dot permutation, let's say np dot arrange, let's say the 10 values, let's say that's our a, let's say this is a, and we want to sort this array. Oh, this is already sorted. Why? Is it sorted? No, it is not sorted. 1/4, it is not sorted. Yeah, let's say we want to sort it. A dot sort. One way of doing that is just call a dot sort and you are done. That's the value of a. Another way, which is sometimes more readable, but although exactly the same, is to use a universal function using np dot that thing. That also is the same thing. Now, sort by default sorts in ascending order. If you want to sort in descending order, then what you can do is you can sort a dot sort, for example. You do that in ascending order. Then what you do is you just reverse it. -1, and just copy that in a again. Now a will be sorted. Wow, sorted in descending order. Yeah, great. Um, one more, just to give you one more flavor. If you create an array, for example, np dot array of strings, for example, a, b, c, and another string is how are you, and maybe we have another string, u785, and maybe we have another string 13er. Let's say that's a string. That is possible. As long as all the objects have same type, you can create an np array. Now you might be wondering, what will do this sort function on a, because these are all strings? Well, the answer is it will sort the strings according to the alphabetic order, whatever the alphabetic order is. Whatever string according to the alphabetic order should become first, that will become first, and the other strings, they will just join. Yeah. So yeah. So that's about something that is not the numeric value. Okay, great. There is a few more things to come about NumPy array, and then we will be moving towards Pandas library that is built on top of NumPy array for better processing of data. Hope to see you in the next video. Okay, in the last video, we saw horizontal concatenation, vertical concatenation, sort function. We also saw some broadcasting and stuff like so. Universal functions, it should be speed here. Sorry, it should be speed. Universal functions are really speedy. I always am talking about NumPy. Whenever I start NumPy, I said it is fast, it is fast, it is fast. I never show you how fast that is. So let me give you an example. Let me just create an NumPy array with a lot of numbers, and then just apply an ordinary function. Let's say I want to add all the numbers in this array B. Let's apply an ordinary function that is not in NumPy, and then let's use a universal function dot sum and see how speed difference is there. If, for example, we apply a universal function to achieve a particular task, how speedy that universal function is, because the vectorized implementation, as I told you, is much faster. How faster? Let's check that out in new Jupyter Notebook. That's a magic command, time it, that will tell us how much time this particular task has taken. And if you run this command, it will call this function again and again several times, and then will report an average value that will be much more stable than just calling once. After that, we will also write our own sum function using loop, and we will see whether that is even closer to a universal function speed or not. Let us just check the speed of universal functions. That will give you a look and feel of how much NumPy implementation is faster. So let's say we have an array, let's say B, np.random.rand, and let's say that array is huge, really huge. Let's say that's the case. Now what we do is let's say we call a function sum. So let's say we call a function sum. That's a built-in function. in NumPy. That's a built-in function. That's a built-in function in Python, not a NumPy function. And then let's say we do the same task using NumPy universal function, np.sum. That's the same as np.sum is the same as if we write, for example, b.sum. So whether you write b.sum or you use np.sum and b pass as an argument, both these things are roughly the same. So let's run it. It will take a while. It will take a time because, okay, the sum function takes 307 milliseconds. That is not a universal function in NumPy. That's Python function. That is not written in NumPy. That is not a vectorized code, nothing. It takes 307 milliseconds to take the sum of the elements of this array. And it does that by applying 7 runs, 7 loops. However, the universal function takes just around 3 milliseconds, 2.7 milliseconds. How are you going to compare this 307 with 3? How much faster you are? Around 100 times you're faster. Yeah. This NumPy is literally faster. NumPy, the universal function, they're faster. Maybe you attempt to know that, okay, this sum function might be too slow. Let me write my own function. To do that, let me define my sum, and my sum just take an argument, let's say something, let's say g, and what it does is for, let's say s equals 0, what it does is for x in g, s plus equals to x, x plus equals to x, and then just return s. Let's say that's your function. Let's say you think that this is really a great function. Let's do that. Okay, let's compute the time for this. Time it, my sum, and let's pass the array b and see how faster this is. This is roughly the same as you're calling the sum function, but this np.sum or the universal function is way faster, way faster. So use universal functions, avoid for loops, avoid your own functions if the same task can be achieved through universal functions. Whenever possible, avoid loops when you are working with NumPy. That's a serious suggestion. Follow that, because the universal function written in NumPy, they follow the vectorized code. All the interpreted slowness that is deferred to the compilation layer, and the NumPy becomes really faster and shows its power when you are working on large arrays using the universal functions. Vectorized implementation, we are now very comfortable that it is always good to use universal functions in contrast to building our own loops and stuff like so. So let's just have a quick tour on just a quick tour of just a few of useful universal functions, including some of the arithmetical functions, some of the trigonometric functions, comparisons, how to handle the missing values properly, basically the nan values inside the arrays. So for example, if you want to add elements of an array, and that array has some nan values as well, so how to handle those, because if a nan value is added to some other value, what will be the result at the end of the day? So we will also just see a few functions that are required for rounding off the floating point numbers. And then we will see primarily that most of these functions that you'll be seeing, they are achievable by operators. There are operators that are overloaded for all these kind of functions, and inside, even in most of the functions, the inside implementation is called by those operator overloadings. So then once the operators are available for most of these functions, why we really need the function names as universal functions as well. So I will convince you at the end by telling you a feature and advanced features in universal functions, that you can set the output argument inside the function as well. which may not be possible directly using operators. So anyways, you will be seeing these universal functions now, and there will be multiple ways of dealing with these universal functions. I mean, there will be multiple functions, there will be operators, all of them, they can do the same stuff for you. So let's start by going towards our friend Jupyter Notebook and just get comfortable with some of these functions. Let me just make this view of the screen a little wider, bigger. Let me just remove the header and the toolbar as well. So now we have better space, better than earlier. Yeah. Um, yeah. So yeah. So for example, let's take an example. Let's say a equals np dot array, and let's have some list of numbers, or maybe we have some, let's say arrange method, arrange, let's say 10. Let's say we have some numbers. Let's say these are these numbers. Now, one way to just add, let's say we have another array b that, let's say np dot random dot rand int, maybe. Let's start from 0 to 10 and make how many elements? Make, for example, 10 elements. So this is b. If you check the shape of b here, that is this. If you check the shape of a here, that is this. Now you might be noticing that the shape of b is 1 by 10. The shape of a is this weird kind of one-sided array. One way to deal with that, if you really want to deal with that, is this NumPy allows you a new access kind of. So let's say, let me call that c equals a. Let's say you want to be consistent with the shape of b. So what you do is you really add new access, np dot new access here, and keep the rest as it is. And now the shape of the c, if you will see, that will be consistent with the shape of b. So whenever possible, I mean, there are certain kind of libraries that requires the arrays to be in a particular shape. I mean, although this is a one-dimensional array, this is also a one-dimensional array, but explicitly adding the dimension or mentioning the dimension is sometimes required for some kind of libraries. In that case, this np.newAccess might be helpful. Just add a dummy access to your array. Okay. Now what we do is we basically add, let's say, the two arrays b plus c, and the result is just in d. We print d. That's okay. Yeah. So that's our d. You can now see if you see the shape of d. The shape of d is again 1 by 10, and it's an array. It's an array with 1 by 10. Again, if we want the same kind of structure back, we can call this np.squeeze function. Yeah, np.squeeze. Where is that? As QUECE, np.squeeze d, and it will squeeze the extra dimension that was there that you have added using this new access kind of stuff. So now if you see this d, it will no longer be an array with double kind of brackets, because here you're seeing if you for example print d, let me print d as the same way as earlier, print d, it is now you can see the array has just one square bracket as compared to the print d as earlier, although I mean that's the same thing one way or the other. The thing that I really want to mention is you have now a, let's say a is this, and you have, let's say, d is this. Both have same number of components. You can add a and d using this. That operator is always there. I mean, NumPy allows you to call the universal functions. For example, np.add, let's say a and d, and you may store the result in some other variable, let's say c. Yeah. So C is there. So C print, or simply C. So C is just the addition. Now, I mean, it is always great to, I mean, use operators whenever, I mean, there is no difference in using this add function or using this a plus operator, because at the end of the day, the add function eventually calls this plus operator inside. So, but that's another way. I mean, if you want really to increase the readability or to use universal functions, there is another way to set the output argument that we will see later on. But you can use the add function if you really want. Further, there is another function, let's say sum, let's say np.sum. And here, let's say you want to add A and D, and you will get the sum in, oh, oops, there's an error. np.sum, only integer scalar arrays can be converted to scalar index. What's the problem? Why we cannot call this np.sum? So let me just see what is A. A is this. What is D? D is this. So np.sum, why not? So it contains A, X's, and oh, the sum is no longer a replacement of add. If you basically want to use the sum, np.sum, it basically adds all the values in a particular array A. For example, here you see A, that's this. And the same thing goes if you want A dot sum. If you want this A dot sum, the same thing goes like that. So, I mean, you should not be using the sum function. If you want to add multiple arrays together, you should be using the function add or operator plus. If you want to operate on a single array and multiple elements of that array, then you should be using the sum function. That's a universal function. Let me give you a more powerful example of this sum function. Let's say we have np dot, let's say A is np dot arrange. Let's say we have 100 elements of that, and then we reshape that into, let's say 2 by 2 by 5 by, let's say that is 2 by 2 4, 4 by 5 20, and 20 by 4. Let's say we reshape that into this 80 elements, and we're good to go. Okay. So now this A is, if you check the dimensions of A dot and M, that's A is a 4-dimensional array. Basically, this A is a 4-dimensional array, which means there are 4 1D arrays. Basically, there are 4 elements, and there are 5 1D arrays, each having 4 elements. And we have 2 these kind of arrays that has 5 1D arrays inside, and then we have, so basically that's a hierarchical structure. If you read it from right to left, 4 elements, there are 5. Now we have an array of 5 elements where each element is an array of 4 elements. Okay, go back. That's a structure now. That's a 2D structure. Now we go back to, now we have 2 structures of this kind. Okay, now if we go back, now we have 2 structures of this particular kind. So that's how this is arranged. If we now say A dot sum, for example, and we set x's as 0, remember always the x is 0 is the first dimension. I mean this dimension. X is 1 is this dimension. X is 2 is this dimension. X is 3 is this dimension, and so on. What will happen basically is, there are 2 structures of this kind, and I'm adding the 2 structures together, and the result will be a 2 by 5 by 4 array. So let's say the result is, if we check the shape of this result, the result is 2 by 5 by 4. That's B. If we further, for example, by the way, I have called this A dot sum. This is the same as calling np dot sum, and then you give argument A, for example. Here, let's call B, and let's do the summation over what axis? Now this is x is 0 for b, this is x is 1 for b, this is x is 2 for b. So if we just specify x is 2, then the result, let's say, is in C. And if you see now the shape of C, that will be 2 by 5. Yeah. So now, for example, let's display C. It's a two-dimensional matrix. Now, if you really want to, if you apply the sum function on x is, let's say, 0, what will happen? What do you think? In x0, it basically add these two, it add all these row wise, which means this particular dimension will just vanish, and the resultant array will be 1 by 5, which means it will be adding the element wise entries of all these rows. So it will be adding row 1 to row 2 element wise, or basically it will be doing sum of every column, and will be resulting that will be giving the result. So that's the result basically. If you just see 172 plus 332, that is 504, 204 plus 364, that is this thing, and so on. So yeah, I mean, universal functions, for example, the sum function, it allows you to operate on a single array, even though you have many more dimensions in that array, and you can just play with that. But in contrast, if you see this add function, it is generally, it operates generally on two arrays, and the same kind of stuff is achievable through a plus operator, although the implementation or the time for a plus operator and the add function, that is the same. Let me show you the time comparison as well. So let's say we have array A, that is np.random.rand. Let's say we have array with array with that kind of values, huge values. Let's say that's n is our, this is our n. Let's say we generate a big array A, and let's generate a big array B, again randomly, np.random.rand, that's n. And what we really do is we say, okay, time it A plus B, let's display the time of that, and then let's say time it np.add A and B. Let's see the difference of times of both of these operators. In one case we use this plus operator, in other case we call this add function. Yeah, so the plus operator takes roughly 8.29 milliseconds on average, and this add function takes 8.24 milliseconds on average, which are roughly the same. I mean, this is because the OS is also running, the other applications are also running, the context switch is happening in operating system and all that stuff. But these two are exactly the same. In contrast, if you apply the sum function, if you for example, if you write your own loop, for example, in your own function to add the elements of A and B, you will be getting a lot of time to do that stuff. And the reason basically is these universal functions, and these they are actually implemented in very efficient way, normally at compiled layer rather than interpretation layer. And here you have seen that whether you apply an operator or you use a universal function, the efficiency, that is exactly the same. And one more thing that I've told you, that even if you call this universal function internally, it calls the implementation of this operator. Okay, so that's about just an operator plus and its corresponding function add. We also saw some beautiful things about this sum function that operates just on a single array. In the next video, we'll be talking more about some more useful universal functions that are much more applicable in general in data science. Hope to see you in the next video. Okay, in the last video, we saw add function and plus operator in NumPy, their speed comparison. We did the speed comparison. We also saw some function that actually takes one input array as an argument, but that array can be very multi-dimensional array, and you can apply that sum on different kind of axes or dimensions if you want. We continue our discussion on exploring more universal functions, just a few more useful functions. And because these universal functions, knowledge of these universal functions actually gives a very good grip to handle data very efficiently, and writing small piece of code, small and smart piece of code, rather than writing big loops and iterating over data and stuff like so. So it is good to spend some time on exploring these universal functions a bit more. So let's go to our friend Jupyter, and let's make an array. Let's say np dot random dot rand, let's say 10. Make another array. Let's say np dot random dot rand, let's say again 10. And what do you think? What will this function do that I'm going to write now? Subtract. What will it do? As the name suggests, it will subtract the entries of a and b. So C is that. Again, you can do the same stuff as C equals A minus B. So this operator minus actually does exactly the same thing. So yeah, so you can do that. Similarly, there's a multiply function if you want. For example, C equals A np dot multiply A and B. And the same is if you want, let's say D equals A star B. The two things are exactly the same, whether you apply this operator or you call this multiply function. Similarly, there is a divide function. There is there are a lot of functions. For example, if you want, for example, to compute, let's say np dot power of a b, so it will compute the element wise power of a and b. So the first element of a raised to the power the first element of b, first element second element of a raised to the power second element of b, and so on, and the result will be raised c element wise again. But the same thing is achievable if you just write that. I mean, that's the same thing, exactly the same thing. The first element of a raised to the first element of b, and all that stuff. So the purpose here is to tell you that there are operators to work with, and there are for example, universal functions, equivalent universal functions to go with. The efficiency is same. Whatever is more feasible for you, you can go with that. I personally recommend, or I personally use operators more than using universal functions. I use only universal functions whenever they're extremely required. Otherwise, the operators, they just do the same job. And to me, they are more readable as well. But this opinion may vary person to person. This is just my opinion. Now, let's say you have, again, you have array A and B, and you just compute the A remainder B. That will give all the remainder values if you divide A from B. Although these are floating point entries, you might be thinking, what do we mean by remainder in that? So let me generate A as np dot random dot rand int. Let me generate, let's say, from 1 to 10, let me generate a 10 values. And if I see the shape of A, that's an array with 10 entries, random integers from 1 to 10. Let me generate another array randomly again. Let's say np dot random dot rand int. Let's say this is again 1 to 10. Let's say the 10 entries. And then what I do is I basically call this remainder. For example, A remainder B. That means element-wise divide the first value of A by the first value of B, and then see what's the remainder. And these are what the entries are. If you really want to see why these are the entries, I can just show you A and B, and these are A and B, and the above is the remainder. So for example, if when 8 is divided by 2, the remainder is 0. When 5 is divided by 3, the remainder is 2, that is there. 2 with 2 remainder is 0, 9 with 3 remainder is 0. When 2 is divided by 8, the remainder is 2, and all the rest of the entries like so. But at the same time, you can use, for example, a mode function if you really want, for example, np dot mode, and that actually take the remainder of a and b element wise exactly the same way as you have seen earlier. So yeah, so you can use these kind of so whether you're going to use, for example, universal functions, or whether you're going to use the operators, wherever the equivalent operators are available, it's completely your choice. There is no difference in efficiency at all. Let me like in the last video, I've shown you the sum function that operates on just one array. Here I'm going to show you another function, let's say mean, or these are called aggregates, by the way. Mean, standard deviation, variance, medians, and all that stuff. So let me just give you, let's say this is a. Let me make another array. Let's say np dot range. Let's say 100 values. Let's reshape them to, let's say 5 by 20. So that's now a matrix of 5 by 20 a. If I call a dot mean, that will do what? If I call a dot mean, if I give axis equals 0, that will take the mean along the very first axis, which means it will reduce this particular dimension. It will vanish this particular dimension. The result will be an array with 20 elements, 1 by 20 array. So let's see that. A dot shape now. Remember, when you apply this operation on a just changes. So the shape of a, the shape of a is 5 by 20. Why is that? When you apply a dot mean axis equals to 0, a doesn't change. Why not? A should have changed. A will only change if I basically replace this a with this particular entry. Otherwise, it will just call a function on a and return the value somewhere. It will not change the a. Wow, that's great. It is important to note. So that is, if I do axis equals 1, for example, the result will be just 5 elements, and which means all the columns, they are just all the columns, they are added together, and each entry is divided by the total number of columns. And in that case, the result is really the 5 entries. So it is good to know how to apply these aggregates that actually reduce dimensions. Here is, for example, a quiz question for you, and we will answer that question next in the next video. So here is a question. I'm posting the question. So let's say we have np.random.rand. Let's say we have let's say 100 let's say 1,000 values dot reshape. Let's say we reshape 1,000 into, let's say 5 by 4, that is 20 by 20 by let's say 2, that is 40. Then, or maybe yeah, 20 by 2, that's 40. So 40 by 40 by 5, that makes 200, and then 200 by 5, that make 1,000, I guess. Yeah, I guess that's 1,000. So 5 into 4, that is 20. 20 into 2, that's 40. 40 into 5, that's 200. 200 into 5, that's 1,000, I guess. Yes. So this A is really a 5-dimensional array. It has 5 dimensions. My question is, what will be the shape of B, where B is the following array? A dot, let's say std. Std is just a standard deviation. If you want to call mean, you can call mean. If you want to call sum, you can call sum. Let's call sum. So sum or mean or whatever, x is equals 3. So that's the result. B is there. The question is, what is the shape of B? I'm not printing that out. What is the shape of B? which dimension just goes on? Which dimension just get vanished? This 5 got vanished, this 4 got vanished, this 2 got vanished, this 5 got vanished, or this 5 got vanished. Which one? What is the shape of the resultant array? One dimension has gone. B is a 4-dimensional array. It is no longer a 5-dimensional array because one dimension is just added up and just collapse and go away. So what's the shape of B? Okay, I end this video here, and I'll wait for your answer, and I will answer that question in the next video. I will answer this question in the next video, but try to solve it. Okay, hope to see you in the next video.